show by substitution into y, that the apple is in the air for less than 1 second. The apple's in the air for less than 1 second. Okay, let's see. I'll leave my diagram there. Excuse me. How do I work out how long the apple is in the air? It'll be from this point, that's when it starts. It's in the air this whole time until y equals 0 again, right? So if I solve for y equals 0, okay, that'll give me, obviously it'll give me the starting point because I start at 0, but it'll also give me the end point in terms of time, right? So here we go, here's my equation, right? Minus 5t squared plus 2 root 5t, that's equal to 0. I can factorize. Whoops. Is that okay there? Yep, took out that negative. Okay, so now I've got my two solutions for t, right? Here's my 0 solution, my starting point, right? And what's my other solution? It'll be 2 root 5 on 5, won't it? This guy and this guy, yeah? And as it happens, he's already rationalized. That's nice. That's just kind of lucky. Okay. So what's his value? It's 0 or, now you have to show that it's less than a second, right? So you have to get out your calculator and you have to chuck the number in. And I think we'll get, what'd you get? You get the same value as me? Yeah, good. Okay. So at this point, you've crunched your numbers, but you need to answer, right? So you would say, Adam catches the apple. Adam's apple, anyway. When, hey, I didn't write the question. When t equals 0.89, right? So it's in the air, the apple's in the air for less than a second. That's all you need to say. Okay. Question? Yes? No? Say it again.
Why does the apple have to be the apple?
Oh, because that's what they asked us to prove. That's all. Show by substitution into y that the apple is in the air for less than 1 second. That's all. And I guess depending on what other kind of, what kind of initial velocity it'll be in the air for a different amount of time. By the way, that's kind of cool because now, do you remember how we did that exercise outside? Right? We did this exercise and we were all trying to make guesses and we did recordings and all that kind of thing. Well, clearly this means if I know this, if I wanted to, couldn't I work backwards to get to my initial velocity? Couldn't I? I could do that, couldn't I? So you'd be able to work out actually how hard you can throw a ball in meters per second. That's kind of neat. Anyway. Okay. Now, part D. Find the greatest height above the point of release reached by the apple. Find the greatest height. Where is it? It's going to be up here, right? That's the greatest height, which corresponds to your axis of symmetry, right? So if I know what the time is here at this endpoint, all I have to do to get to the maximum is to take half of that. That's all I need to do, right? So let's do that. When the time is half of that, root 5 on 5. That's 1 on root 5, isn't it? Okay? And I want to know what the height is, so which of my equations, of which I have many, is the relevant one? It's y. Good. Vertical displacement. So I've got this. Okay, where's my equation? Here it is, or there it is. So I've got minus 5, 1 on root 5 squared, plus 2 root 5 times 1 on root 5. Is that all right? What happens in here? Simple numbers because they chose a simple situation for us. Okay. Part E, we've already done half of. Part A, they say show that the flight time is 2 root 5 on 5. Well, we've done that. That's fine. But then they ask us to find the horizontal distance traveled by the apple. That's this distance. How do I do that? I'm doing the same thing, right? But I'm not subbing into y, right? I'm going to sub into x. I'm just leaving this here because I need my horizontal displacement equation, right? So I can say this is my final point in the motion of the apple, so I'm going to chuck it in. And because it's root 5 and root 5, you just get 2, don't you? There you go, 2 meters away from each other. Easy, right? Okay, find x dot and y dot at the time at the time Adam catches the apple, okay? How do I do that? What am I up to? I think I'm up to f. How do you find x dot and y dot for the final point in time? Well, again, I'm going to look at my x dot equation and my y dot equation, which I rubbed off, which I think is something like minus 10t plus 2 at 5, I think, from memory, okay? So you're going to pop in your final time into both of these, okay? That'll give you x dot and y dot, but what they really want to show is the second part. Use a velocity resolution diagram to show the final speed, don't care about direction, show the final speed equals the initial speed. Have a look at this, by the way. You can kind of see it, can't you? There's this symmetry about the diagram, because it's a parabola, right, that you're getting this kind of situation over here in reverse, right? So therefore, in terms of speed, they will be the same, because I don't worry about direction, okay? So, go through it with me. How do I set this out? I'm going to take this time, right, and I'm going to pop it into here and here to get my x dot and y dot. We can do this in our heads, can't we? Tell me what x dot is. Root 5? Root 5?
Yeah.
It's a constant. Y dot? This is going to be, it'll be minus 4 root 5 plus 2 root 5, won't it? That was the minus 20 on 4, I think. And that's minus 2 root 5. Can you see what's happening? Right? Horizontal velocity hasn't changed. Whole situation because of this, right? Vertical velocity is exactly what you started with, but in the opposite direction. Of course it is, because it's coming to land, right? So now when you do your diagram, this diagram's a crucial part of it, okay? Okay, now the apple's coming down. Like so, right? So here's your x dot. And here's your y dot, which is negative. Okay? But of course, Pythagoras squares, everything gets stripped out. So when you get this speed here, it's still going to be 5, right? Okay, now, important little note. I got a question about this at the end of yesterday's lesson. You've got 2 angles in this situation, right? Now, this question talks about, excuse me, the final angle of inclination. Stop. Angle of inclination. Where is that on this diagram? Now, I think the final angle of inclination is here. I think that's the angle of inclination. You go from the horizontal, and you think about how far you have to look up, right? That's an angle of inclination. That's what they're asking for. In this case, it would be negative 10 inverse of 2. Negative 63 or whatever. You can crunch the numbers, you can see, right? But there's another angle here, and it has a different name. This is the angle of inclination. But the other angle, which they will ask for just as often, is not the angle of inclination. Of course it's not, because you're not looking up at this point. You're doing Pilates at this point, okay? This is called the angle of impact. It's obtuse, right? Unless you're firing in the opposite direction, it almost certainly has to be obtuse, right? So if they ask for the angle of inclination, this is what they're after. Or alternatively, the angle of elevation, same thing, okay? But the angle of impact, right? Come back to the circle. By convention, when we're measuring angles like this, we always measure from which point? Where's 0? No, seriously, where is the 0 angle? It's from the positive side, this side, of the x-axis, right? The positive side. You don't measure it from over here. It's not enough just to say from the horizontal. It has to be from a direction of the horizontal, right? So in the same way, your angle of impact is from the positive side of the x-axis, okay? So note for that, because they'll ask you different things and they'll be expecting a different angle, okay? I guess it would be, if they did ask for it here, it'd be 117, thereabouts. You get the idea. It's an obtuse angle is my point, okay?